Right. So last time we finished talking about the electrostatic potential. This is V, has units of volts. And I indicated that just like the electric field, the electrostatic potential has the superposition property. So that means if you find the electrostatic potential from one charge, and then you have the electrostatic potential from a different charge at the same location, then you can just find the electrostatic potential from both of them by combining them. So we're now going to keep going a little bit deeper and talk about the electrostatic potential a little bit further. So let's ask the question, how are E and V related? V being the electrostatic potential, E being the electric field. So first and foremost, we can just start jotting things down, similarities that they have. Or maybe not jotting things down, but so they both result from some charge distribution, right? So if you have a whole bunch of charges arranged in some fancy way, then the electric field is completely determined by how those charges are arranged. Similarly, if you have some charge distribution in some fancy way, the electrostatic potential is also completely determined by that distribution. So they both are a result just of the distribution of charges, not of like the test charge or anything. Sorry. The electric field, unlike the electrostatic potential, the electric field relates to the force on the charge. The electrostatic potential relates to the potential energy, right? You multiply the test charge by the electrostatic potential, you get that, I don't know what's wrong with me. You get that test charge as potential energy. If you multiply the test charge by the electric field, you get that test charge as force. And that's the important one. So here we have that E relates to force. God, I don't know why I can't write on a straight line on this computer. And V relates to energy. And we know that there's a relationship between the force on something and the energy, the potential energy of that thing. So just as a quick reminder, recall that the change in potential energy of a system, which we might write as UB minus UA, that's just the negative of the work done going from place A to place B, which is just the negative from A to B of F dot dl. Right. So we can plug in that U is equal to QV. That's just the definition. That's the definition of V. It's just the energy of a test charge divided by the test charge. And we also can plug in that the force on a test charge is equal to the test charge times that electric field to get the following. VA minus VB, notice how it's reversed from VB minus VA because there's a minus sign, is equal to the integral from A to B of E dot dl. And so this is how the electrostatic potential is related to the electric field. Also note that this relationship is why we use volts per meter for the electric field. In the past, we defined it as newtons per coulomb, but volts per meter is more commonly used. We just reverse it because there's a minus sign here. So we can put that minus sign on the other side and make it VA minus VB instead of VB minus VA. And so it's volts per meter because this has units, the left-hand side has units of volts, the right-hand side has units of whatever the units of E are times meters. So electric field units times meters is volts. So the electric field has units of volts per meter. The reason why we do this is because talking about electric fields and voltages is more important than talking about charges and forces. Hence why we don't prefer the newtons per coulomb notation. But they are the same, they mean the same thing. Like 1 newton per coulomb is the same as 1 volt per meter. They're the same quantity. Now, I want you guys to notice something about this integral. If the electric field points in the same direction as the path vector, i.e. they're parallel, the path vector is dl, by the way, then the integral just becomes a product sorry, it becomes a product, and in particular, it's positive. It's a product of magnitudes. Think of it this way. If you have two vectors and they point in the same direction, the dot product of those vectors is always positive. So if E points in the same direction as dl, then the dot product of E dot dl is always positive. And so if you do an integral of something that's always positive, you get something positive. And so what that implies, if the electric field points in the same direction as the path, that VA is greater than VB. And so we might phrase this scenario as saying that there is a potential drop from A to B. So if you put a charge at position A and you let it go to position B, then the potential that it experiences decreases, it drops. So there's a rule of thumb that we can derive from this relationship. That rule of thumb is pretty nifty. It's that electric fields point in the direction, of decreasing electrostatic potential. So all this says is if E points in a direction such that the potential energy drops, sorry, the electric potential drops, then that means that the direction of decreasing electrostatic potential is the direction the electric field has to point. We can make that rigorous too. So first, just a quick recollection, a quick thing to remember from 9A. Hopefully you remember this. We saw the following in 9A, that if delta U, the change in potential energy, is the negative of some line integral f dot dl, where f is just some force, then that meant that the force is the negative gradient of the potential energy, right? And so the same reasoning applies here. All we did is we just replaced some letters. So we have here that the electric field is the negative gradient of the electrostatic potential. And that's a super powerful equation, because it turns out calculating the electrostatic potential is way easier than calculating the electric field. So if you can find the electrostatic potential, then all you have to do is take a few derivatives and you get the electric field wherever you knew the electrostatic potential. It's remarkably powerful and will be your best friend for computing things. I actually laid out there's an example that I linked to in the lecture notes. This is an example of calculating the electric field from a point charge using the electrostatic potential. You guys already know the electrostatic potential for a point charge. I think we went over that on Tuesday. And then you can take the derivative of that, the appropriate gradient, and you get the electric field miraculously. It kind of just pops out, and that's really convenient. Now, depending on what coordinate system you're in, how the gradient is defined, the gradient operator, is different. So like in Cartesian coordinates, it's just the sum of the partial derivatives in their respective directions, right? So it'd be like ddx in the i hat direction plus ddy in the y hat in the j hat direction plus ddz in the k hat direction. In spherical coordinates and in cylindrical coordinates, it's a little bit different. But there is a discussion of this in the Libre text. It's about in the middle of section 2.2. I'm not going to go over it because I don't have that time, but I do want you guys to take a look so you're familiar with how to take the gradient in different coordinate systems. It'll just be a useful thing. There's another aside that I'd like to talk about, which is this business about conservative fields and curl-free fields. So let me just, we're just going on a little math detour right now. So if you have a conservative field, i.e. it produces a force that's conservative, or maybe it is a force field and that force is conservative, that means that field is curl-free. So just to be more specific about what that means is the following. So if the following three things are equivalent, or the following, I can't write today, I'm sorry. The following three statements are equivalent. And you guys learned about conservative vector fields in math, right? So this shouldn't be particularly new, but it's a good refresher. So first, F is conservative, and this is just for any F, or for any E or whatever, any vector field. So that statement is equivalent to the statement that F is the negative gradient of U for some U. There is some function U that F is the negative gradient of. And then the third thing that's equivalent to the above two things is that the curl of F is 0. So basically, one way that you can check if a force field or an electric field or whatever is conservative is by taking its curl. If the curl is 0, then it's conservative automatically. Similarly, if it's conservative, then that means that there is a function that whose negative gradient is the field. And so this is just a useful set of mathematical relationships that lets you go between these three different ideas. And the reason why this works is just because the curl of the gradient of any function is always 0. So if you were to replace F with a negative gradient of U, that's just by definition 0. Not by definition, but you can show it relatively easily. So the end result of this mathematical aside is that because the electric field has the property that it's the negative gradient of a function, V, we have that the electric field is curl-free. And in fact, this is probably the most, or this is the electrostatic equivalent of one of Maxwell's equations. So this is kind of a big deal that the curl of the electric field is 0. All right, one more aside, and then we're going to proceed. Well, actually, this one's less of an aside. This is a useful discussion. So we have to talk about equipotential surfaces. Now, hopefully you guys talked about that in 9A. So we're doing something similar to what you guys hopefully saw in 9A. But if you didn't see it, then we'll have to then go back and read up more on it. So, oh no, Menon. So we've already established that that the gradient of a function, or perhaps you guys know this, that the gradient of a function, maybe you learned it in a math class, points in the direction of steepest descent. Now, what that means is if you have some function, maybe the function tells you the height of the height of a mountain. Maybe it's the altitude at any given position, right? That's a function, takes in a position and outputs a number. If you took the gradient of that function, that would give you a vector. And the direction that that vector points in would be in the direction that increases your height the fastest, hence steepest, in the direction of steepest ascent, i.e. the direction that increases the value of the function the fastest. And so what that tells us about the electric field is that the electric field points in the direction of steepest descent because it has a negative in front. And this is of the electrostatic potential function, which is already agrees with the rule of thumb, right? The rule of thumb is that the electric field points in the direction of decreasing V. And it's not just it's any direction of decreasing V. It's in the single direction that decreases V the fastest, there's only, I mean, except in some very degenerate cases, there is only one direction that decreases the field the fastest, in which case the electric field points in that direction. So with that in mind, let's kind of do a thought experiment. So let's say that you have a situation where there is some electrostatic potential. So let's write this out, because we're going to try to learn more about how these things relate to each other. So suppose you evaluate, or suppose you know, the potential V everywhere. And this is just for some charge configuration. Like there's just some charge configuration you've gotten out and you've measured the potential at every position in space. So if you examine a particular point in space, the values of the potential function, of the electrostatic potential function V, nearby that point will be close to the value that you measured at that specific point. This is just a statement about the continuity of the potential function. All that means is that, like, if you start at one point and then you move a very, very small distance away from that point, the potential is only going to change by a very, very small amount. This is just continuity, which you should have learned about in math class. However, if you move in the direction, if you move in the same direction as the electric field, i.e., so you know what the potential function is, so you can find the electric field. If you move in the direction of the electric field, so the picture here is like, the point of interest is this point P, where you know the electrostatic potential, and maybe you're measuring nearby points where you know the electrostatic potential nearby in a small circle around it. If you move in the direction of the electric field, what that would mean is that of the points that you chose nearby, the electrostatic potential here is the lowest. So if you looked at all the points nearby your point of interest, the one that is in the direction of the electric field from your point would have the lowest electrostatic potential. And if you move in the direction opposite the electric field, so say here, we would have that the electrostatic potential is largest, because opposite the direction of the electric field is the direction of steepest ascent. It's where the electrostatic potential increases the most. And if you move in some perpendicular direction, say this direction, then the electrostatic potential is the same. That's a terrible V. It's unchanged. And that's just because and this should be something that you can visualize. If one direction increases and the opposite direction decreases, then there will be some midpoint where it's unchanged. And that midpoint is precisely the perpendicular from the electric field. That is the intermediate value theorem that you guys should have covered, that you guys should have learned at some point in calculus. Again, most of 9C is calculus, so yeah, there's something to be said about understanding that stuff. And so it turns out that you can map out all of the points in space where the electrostatic potential is unchanged. So let's say that everywhere that I'm going to mark with an X, or you know what, I will mark it with like green. Everywhere that I mark with green is a place where the electrostatic potential is unchanged. So there would be a point on either side, right? And so then let's say we go to this point and we do the same thing. We figure out which direction the electric field is from that point, and then we go in the direction where the electrostatic potential is unchanged. Maybe that's here. Then we do the same here. And we just start marking out all of these points where the electrostatic potential is unchanged. Eventually, you will fill out a surface. In this case, this is a two-dimensional picture, so it's a line, but you can imagine it'd be three dimensionals. There'd be a whole surface of places where the electrostatic potential is unchanged. And that means that the electrostatic potential through or on that surface, in this case on that line, is constant. So let me just write out some words so you guys can see something more explicitly. The space of all points that have the same V, the same electrostatic potential, form a surface. And that surface is called an equipotential surface. And you can probably guess where the name comes from. It's a surface, and on that surface, all the potentials are equal, right? Nothing too sneaky there. But the consequence of this fact that such surfaces exist means that you can map out a path on a surface or on an equipotential surface. And so if you were to do that, if we travel along a path that always stays on an equipotential, by the way, sometimes we drop the word surface, we just say an equipotential, but that's just language, that always stays on an equipotential, and it starts and stops on an equipotential, from A to B, then the following is true. We would have the difference between the electrostatic potentials, VA and VB, that should just be 0, right? Because the potential values are the same on that surface. But we also know that the difference of those electrostatic potentials, that's given by this, where is it? It's given by this line integral here. Sorry, here. It's a line integral from A to B along some path. E dot dl. And so the only way that we can have that 0 is equal to some integral, where the integral is a dot product, the only way that this could possibly be true is if the electric field is perpendicular to the path vector everywhere on the path. That it's a 0. And this is true about every path on an equipotential surface, which means that the electric field is just perpendicular to equipotential surfaces. So you have a surface, maybe here's your surface, and then you have another surface lower down, and you have another surface lower down, and so on. The electric field has to point perpendicular to that surface, always. On every equipotential surface, the electric field has to be perpendicular to it. Yes, that does mean that the equipotential surfaces would make very, very good Gaussian surfaces, right? Because it's a surface that you're already given, and the electric field is always perpendicular to them by definition. That said, equipotential surfaces are not always particularly nice looking, so sometimes they're hard to do integrals over. But there's another. Is there anything we can say about the magnitude on the surface? The magnitude of what? No, there's nothing. No, you can't necessarily say that the electric field is constant there now. Well, actually, yes, we can say something about the magnitude. The magnitude has to be constant on the electrostatic or on the surface, if only because if it weren't, that would mean that you could go along the surface and the electric field would change. But by definition, it shouldn't. Like that would mean that. Yeah, I'm pretty sure. I'll think about that. We can talk about it more afterwards. But I'm pretty sure it means the electric field should be constant along that surface. But these aren't particularly useful to be Gaussian surfaces anyway for more complicated reasons, just because they're typically hard to figure out. Usually, you have to know the electric field before you know the equipotential surfaces. Right. There's another consequence of this fact, though, that the electric field is perpendicular to equipotential surfaces. The fact is that we also know that the surface of a conductor always has electric fields that are perpendicular to it. So the surface of a conductor, the electric field is always perpendicular to the surface of a conductor, which tells us automatically that conductors are equipotentials. The entirety of the surface, or the entirety of the surface of a conductor, is a single equipotential. And in fact, it's not even just the surface of the conductor that's the equipotential. It's the whole conductor, the whole three-dimensional thing. And the reason for that, perhaps you should think about, but it boils down to the fact that the electric field inside the conductor is 0. So how could the electric potential change inside the conductor if there's no electric field to do the changing for it? So perhaps think about that one a little bit more. I'll leave that to the reader to figure out. So this is great. We've talked a lot about electric potentials, but there's more to do because I promised that they're useful. So let's actually start using them. These are, I did say that these make solving problems remarkably useful or remarkably easy, so we're going to do that. So the first example that I'm going to do is the same example that we did, I think it was on like the second lecture of the quarter, where we did the electric field the electric field some distance r from a finite line of charge. So we did that example before, and it was kind of messy. We had to like, we drew up a, let me draw it out. We had our finite line of charge, we had like a little chunk of charge, and then we had to make arguments about symmetry so that the, like if we were at this point, P, we had to make arguments about symmetry, and we had to deal with adding up the vectors to and then we would pair this one with another one so that the vertical components of the vectors cancel out, but the horizontal components don't, and so on and so forth. But, and because we had to make those sorts of arguments, we never really asked, what about the electric field, say at this point, at say the point RZ, where we are at, sorry, let me draw this higher, where we are Z units above the center line. We never really computed that because we didn't really have the tools to do so. It would just make the problem really hard. So we're going to do that now. We're going to be able to solve that problem, figure out the electric field at this point now, rather than just at the center line, using electrostatic potentials. So this is Z units above the center line. So our goal first is to find V of R and Z so we can compute the electric field by just taking the negative gradient of V. So that's what our goal is going to be. It's going to be to find this electrostatic potential first. So let's do that. First, let's give this small chunk of charge dq, let's give it a different coordinate z prime, because I'm already using z for the position of the point of interest. This distance here, this distance is r. Oops. This distance would be z minus z prime, sorry, z prime minus z. And we don't even have to worry about the other side anymore. We just, like, we don't need that as a calculational tool. So first, let's start answering some questions. So how far, so by the way, what we're going to do is we're going to find the electrostatic potential from each of these tiny chunks of charge and then add all of those up because of the superposition property. So in order to do that, we need things like the distance that chunk of charge is from our point of interest. We need things like how much charge that chunk of charge has, and so on. So let's start answering questions. So how far from the point RZ is dq? Well, we're going to call it capital R. And so using some relatively basic trig, we find that capital R is the square root of r squared plus z prime minus z quantity squared, right? It's just Pythagorean theorem. So just like before, when we did the electric field, we also need to know how much charge there is in terms of our variable z prime. Oh, by the way, we're going to assume the whole thing has constant uniform, constant linear charge density, lambda, length L, because this is a finite rod. Length L, charge Q. These are just all the things that we're assuming, the standard business. So the amount of charge, because it's a constant, well, actually, this is just true regardless for any linear charge, it's just lambda dz prime. It's the length of the chunk times the linear charge density. And because it's infinitesimal, it doesn't matter whether lambda is constant or not. Then we can use our definition of V from a point charge. For a point charge, the amount of electrostatic potential that you have at some position is relatively simple. It's just the amount of charge divided by 4 pi epsilon naught times the distance. And so we can treat this small chunk of our rod as a point charge because it's infinitesimally small. And so we have that dV, the small contribution to the electrostatic potential that we get from this small chunk of charge, is just dq divided by 4 pi epsilon naught capital R. And that's just, it's capital R because that's the distance. That's a very curvy distance. The distance here. And so we're going to have to replace that with R squared, with the square root of R squared plus Z minus Z prime squared. By the way, just as a quick aside, this formula, this implies, this is only a valid formula if we choose a reference point at infinity, a reference or 0 point. I.e., if you were to plug in, remember when we were initially defining the electrostatic potential energy, we needed to make a reference point. We decided that the potential energy should be 0 when two things are infinitely far away. You have to make a similar choice for the electrostatic potential, and that choice is made here, because if the distance was infinite, then the amount of contribution, dV, would be 0. But we could have chosen another place where the contribution would be 0, and we would have done that just by adding a constant. If you add some constant, there will be another distance r, maybe subtract the constant. There would be another distance r, let's call it v naught, where the potential energy is 0, but it wouldn't be 0 infinitely far away. Yeah, that's dz prime. So it's infinite because we want to divide. No, we don't want it to be 0. I'm just saying that this is a choice you made, and it's a common choice that you make. But later on in today's lecture, we're going to have to make a different choice. So I'm just foreshadowing that. It's dz prime because z is just some parameter that describes the point of interest here. We're not going to be integrating over z. We're integrating over z prime, which will add up along the rod. Right, so now we just combine all of these things. That's a lambda. There are no x's in this problem. Now we just combine all of these things, and we get the following. We get that v of r and z is an integral from minus L over 2 to L over 2. Remember, this is a finite rod, of lambda dz prime divided by 4 pi epsilon naught square root of r squared plus z prime minus z squared. So again, notice that z and r are constant here. They just tell us where a point of interest is. The thing we're integrating over is z prime. And so this integral turns out to actually be kind of nasty to do. I'm not going to show you how to do it. I used a computer to do it, but it can be done using lookup tables or using an integral table or using Wolfram alpha or whatever. And the answer that you end up getting is the following. You get that v of r and z is lambda over 4 pi epsilon naught times the log of square root r squared plus z minus L over 2 squared plus L over 2 minus z divided by square root r squared, and I'm going to make sure that I get the right sign here, r squared plus z plus L over 2 squared minus L over z, minus L over 2 minus z. So that's what the potential is. It's just this nasty, horrible function. Like, it looks like it's hard, but at the end of the day, it wasn't that hard to set up. All we did was we wrote out what our infinitesimal potential was. We figured out what dq was. We figured out what r was, and then the integral is set up for us. Then we just write out what our integral is, and we plug everything in. The hard part then is actually doing the integral. But once we're here, once you can, yeah, now you just have to do a gradient. And so a gradient is, so maybe you guys have this feeling, but I have a similar feeling that generally integrating is hard because you have to kind of be clever about how to do it. But taking the derivative of something it might take a long time and it might just be messy, but it's mechanical. Like you never have to think too hard about it. You just do it. You just apply the chain rule, apply the product rule over and over again until you're done. So, so now you can just do the gradient, and that's just a math problem at that point. So we get that the electric field of r and z is the negative gradient of v of r and z, and then we would just take the negative gradient of this thing. Now we would want to use cylindrical coordinates here because this is a cylindrical coordinate problem. We have a radial direction r and then a Cartesian direction z. And so in this case, the cylindrical coordinates, what were we integrating with respect to for that integral? I mean, it's dz prime. That's why there's a z prime there. Right, so the electric field in cylindrical coordinates is just minus partial of v with respect to r in the r hat direction, minus partial of v with respect to z in the k hat direction. And that's it. No, but you'll be given an integral. You'll be given an integral table, like a table of integrals that you can use as a lookup tool for the exam. And so just as a, so I'm not actually going to do this computation because it's messy, but if you want to see it, you can look at example 2.3.1 in section 2.3 of the LibreText. So now you might say, okay, that's great. That's just an answer. And you'll find, by the way, that this is now the electric field everywhere at any particular place in space, not just at the middle point. So this actually got us an answer that was otherwise hard to do. And so you might say, oh, so this is a useful tool. It's messy, but it's a very useful tool. It can solve hard problems. So what if we wanted to do the same thing for an infinite line charge? So for an infinite line charge, let's just blaze ahead. We would just take the limit as L goes to infinity, right? Not argument. So you might just naively take v of r and z to the limit as L goes to infinity of v and r and z, and then take the derivative, right? You would just do that, and then take the negative gradient. But that doesn't work. I shouldn't cross out no. It doesn't work, and the reason it won't work is because when you take the limit as the length goes to infinity, you will get infinity out. You won't get anything that depends on any variables. It will just be the limit as L goes to infinity of v and r and z is infinity. So how do we take you can't take the gradient of infinity, so we have to do something different. So the way that we resolve this potential paradox-like thing is, well, actually, let me explain why this becomes an issue. So the problem arises because the limit as, say, x goes to infinity of the log of x is infinity, right? So and this is effectively the log of something that we're taking as that something goes to infinity. So that's why this is a problem. So how do we
I have a question.
Yeah.
Okay, so what if our function of r and z, or whatever parameters we're using, what if it's not a natural log function? Could we then?
So yeah, then you could do that. This is a very specific problem to the line charge.
Okay.
Which we're going to fix. Yeah. So to fix it, we can realize that we had freedom in our choice. We chose here that the electrostatic potential should be 0 infinitely far away. But that doesn't make a whole lot of sense when you're going to end up with a logarithm. You don't want it to be 0 infinitely far away, right? So what we're going to do, and the reason why this hurts us is because if it's 0 infinitely far away, but the log of something as you go infinitely far away is infinity, then that means that it had to be infinity everywhere except infinitely far away. It becomes a problem. So instead, we just choose a different place to call it 0. Pick a different reference point, and it fixes the problem. So let's say we want that v equals 0 at the position r0 and 0. So we just want to call it 0 there. We can just choose that. It's just an arbitrary choice. It doesn't actually matter. So let's do that. So in that case, dv becomes dq over 4 pi epsilon naught r minus dq over 4 pi epsilon naught r0, where r0 is the natural thing. where r naught is the distance to that point. It would be the square root of r naught plus z squared, or plus z prime squared. So if we do that, if we choose that for our dv, then we do the integral the same way that we did before, and we would get that the potential, the electrostatic potential, it's just this distance here. There, it's just some arbitrary point that we chose, some place where we want the electrostatic potential to be 0. If we do that integral, then we end up with, I need more room than that. We end up with a horrible, horrible, horrible function, but it solves our problem for us. We get lambda over 4 pi epsilon naught. I'm going to go up here and steal this, because the first term remains unchanged, right? Will you please copy? Okay, I'll just write it because it's not wanting to work. So it's the log of the square root of r squared plus z minus L over 2, quantity squared, plus L over 2 minus z, divided by square root of r squared plus z plus L over 2, quantity squared, minus L over 2 minus z. So it's that term, that's the first term, minus the log of square root of, that's a terrible square root, square root of r naught squared plus L over 2 squared, plus L over 2, minus square root of r naught squared plus L over 2 squared, minus L over 2. So that's what our new electrostatic potential looks like. And you'll notice that this is just the old one plus a constant, right? And you can always add a constant to potentials. You guys learned about that in 9A. And so now you can go and check. It's easy to check that, and you do this just by plugging in, that v of r naught and 0 equals 0. That's just a check that we can now make. But if you were to plug in, say, r is infinity, then you wouldn't get 0 anymore. And that's just a trade we made. We just choose to make it 0 somewhere else. And so, now we can actually ask what happens when we take the limit. So what is the limit as L goes to infinity of v of r and z using this formula? Well, there's a bit of math. It's in section 2.2 of the online textbook. But the end result is you get that this is equal to lambda over 4 pi epsilon naught. You have to do some L'Hopital rules and stuff like that. It's a little bit nasty. Times the log of r naught squared divided by r squared, which is just equal to lambda over 2 pi epsilon naught times the log of r naught divided by r. The log rules how you can move powers over to a coefficient, all that business. And so even when you take the limit as L goes to infinity, I'm going to call that v infinity. If you evaluate it at r naught and 0, that's still 0. In fact, even if you evaluate it at r naught and z, it's 0. And that's just because when the rod gets infinitely long, the z-axis doesn't matter anymore. And so now we can evaluate this. We can evaluate the gradient of that to find the electric field. The electric field is negative the gradient of, say, v infinity of r and z, which is just negative dv dr in the r hat direction because it has no z dependence anymore. And hopefully you guys know your derivatives of logs. This is just lambda over 2 pi epsilon naught r in the r hat direction. And that is the answer we got for an infinite line charge in the past. So this particular phenomenon where you have to choose a different 0 point doesn't happen often, and it typically happens because there's a logarithm involved. So like if we were doing this for a, if we were doing this for like a sphere of charge or something like that, you wouldn't have to worry about that. But this is a tool that you guys should have in your toolbox that you can always choose a different 0 point to maybe make your answer work. But at this point, now it's just a matter of doing a whole bunch of practice, right? You just, you pick some charge distribution, you go and you compute its electrostatic potential, and then you can take a gradient and find the electric field. And it makes problems a lot easier because that you otherwise may not have wanted or been able to solve. Because generally, doing derivatives of an integral is easier than doing integrals of a derivative. And when you're finding the electric field directly, you're doing integrals of a derivative. It just makes things nastier. So we're going to change gears now and talk about a different topic, but it will relate to the electrostatic potential. The electrostatic potential is like one of the most important things that you can learn about in E and M, because it's a really useful tool and a really useful way of describing how electric fields work in a cleaner way. So keep that in the back of your head. We're going to change gears a little bit. We are going to talk about capacitance. Right. So let's just thought experiment this. I have to keep writing though. So let's suppose that we have two charges, or we have two conductors fixed in place. Conductors fixed in place, like they're glued down or whatever, and they're both neutrally charged. So they're both neutrally charged. They have no net charge. I'm just going to draw a picture. Here's conductor B. Here's conductor A. Okay, so far so good. Now imagine that we remove now remove plus Q from B. So take some amount of charge, some positive charge from B, and place it on A. So we're taking Q, we're bringing it over from here. Now B has total charge minus Q, and A has total charge plus Q. All we've done is, like, the total charge of the whole system is still 0, it's still neutral, but we've separated the charges a little bit. So in this configuration, the field lines are going to be complicated, right? Like, these are some randomly shaped conductors, so figuring out the field lines is challenging. But we do know one thing. We do know that inside of the conductors, so I'm going to put A here and plus Q, and B here and minus Q. Inside the conductors, there are, yeah, these are two beams. There's no electric field. And we know that there should be no net flux leaving both conductors. Like, if you consider both conductors to be a single system, there should be no net flux leaving that combined system. What that means is that every electric field line that starts on A has to end on B. And we know that the electric field lines exit and enter conductors perpendicularly. And so the end result is that the electric field lines they'll have some complicated shape, but it'll look something like this. And so on, right? And there will be more coming out from the other sides that join back further away. But the electric field lines will be some complicated thing. It might look like a dipole if the shapes are nice enough, but otherwise it might look like some complicated thing. There might be some wiggly boys in here or something. And they just are what they are based off of the shape. And so now let's think a little bit about what happens to the electric potential between these two beams, right? So recall from 20 minutes ago that V decreases fastest along the electric field lines. So if you traveled along these lines, your V is decreasing the fastest that it could possibly decrease. So if we do a line integral along one of these paths that the field lines map out, the resulting difference of electrostatic potential would be given by the following. VA minus VA, that's the electrostatic potential difference. It's just an integral from A to B, and I'm going to say that this is along some particular electric field line. It doesn't matter which one, but it has to follow one of them. The electric field dotted into the path length, this should be greater than 0. It has to be greater than 0 because we're moving in the same direction as the electric field, as we talked about earlier. But just as a caveat, because the electric field is conservative, it doesn't actually matter what path we take to go from A to B. We could have taken this path, maybe that electric field line path, or we could have taken this path, or we could have taken this path, or any path. Any of the electric field line paths would have to result in the same overall difference of potential, because conductors are equipotential surfaces, and the electric field is conservative. So the question is what happens if we just double? I'm going to call this delta V, by the way. What happens if we double Q and minus Q? I.e., we just take Q more charges from B and put them on A. So now you have minus Q, or minus 2Q on B, and plus 2Q on A. Well, we know that the field lines, the shape of the field lines, those aren't really affected by the amount of charge. It's just affected by the shape of the things, right? Because the field lines, the geometry of them is kind of fixed by the fact that they have to be perpendicular out from the surface. So the field lines, if we double the charge, they won't move. They just get stronger. And so what that entails is that the electric field, when we have two charges on either, or 2Q on either of the conductors, should just be twice the magnitude of the electric field from one of those charges. And so so with that result, we can actually go back and see how the electric potential changes. The potential difference has to double, in fact. So delta V 2Q would be an integral from A to B. It's the same, it's along the same path because the line in the electric field lines aren't moving. But now we're integrating over the electric field from the 2Q system. But we know that that electric field is just twice as big. So this would be 2 times the integral of the electric field with 1Q. And that's just 2 times the change in the potential. So the point is if we say we triple the amount of charge on each one of these, the electric field lines stay in the same place, but they get 3 times stronger. So the electric potential difference gets 3 times stronger. So what this seems to indicate is that the potential difference between the two beams, the conducting beams, and this really is the potential difference between the conducting beams because everywhere on the conductor is at the same potential. So if you measure the potential here and here, it would be the same as measuring it here and here. What this says is that the potential difference between the two conductors is proportional to the amount of charge that is separated by them. So I'm going to write this out in words, what I just said. So for a given pair of conductors in some spatial configuration, doesn't matter which one. Well, they have to not be touching, but besides that, the potential difference between them is proportional to the separated charge. Sorry, my handwriting's getting worse. I've been writing a lot today. In math, this is just saying that the separated charge, and I'm going to leave out this subscript separated from now on, but I'll write it here. This is proportional to delta V. Or, put another way, Q is equal to C times delta V, where that C, it's just a constant. C is a constant that is specific to a particular spatial configuration. Particular to a specific spatial configuration. So if we moved these beams around, that constant C would change, but it would still be true that whatever the potential difference was, if you doubled the charges, you would double the potential difference. So like if you changed the distance, or if you rotated one of them, or you made one like a different shape or whatever, it would change that constant. But for any particular spatial configuration, there is a number, C, that tells you how much to multiply the potential difference to get the charge separation. The reason why this happens, by the way, is that changing the geometries changes how these electric fields wiggle. So you might travel over a longer path, or maybe the electric field decreases in magnitude along the path because you separated them further. And so the end result of the potential difference might change, but regardless of how it changes, if you keep the spatial configuration fixed, changing the charges changes the potential difference proportionally. Yeah, so all we're talking about is it's basically the difference between the charges divided by 2. That's the Q that we're talking about, and that's the Q that we're always going to talk about. You could also think of, like, it's the same when we talk about the charge of a dipole. It's the difference between the charges divided by 2. Now, you could talk about a system that has net charge and then also has separation of charge. So maybe one of them has 2Q and the other one has 4Q. The separation would still be, the separated charge would still be Q. It's just the whole thing is charged now. So the potential difference would still be the same between those 2 points, but now there would be a net potential between the whole thing and any other point. Anyway, so let's talk about that number C. So the units of C are just exactly what you would expect from this relationship. It's coulombs per volt. And it's given a special name. It's given the name farad or farad or whatever, and it's abbreviated, the SI abbreviation is F. It's named after some guy, probably a French or Italian guy. That's usually who these things are named after. And and you might realize that a single coulomb is really, really big. So if you had a 1 farad thing, if you describe a system with a constant of 1 farad, that would be a really, really huge number of charges separated for a single volt of potential difference, not named after Faraday. I don't think. It's coulomb, sorry, per volt. And so typically most real world applications of this idea of C, oh, is it named after Faraday? Okay, cool. Usually most real world applications will have measures of microfarads or smaller. Like there are such things as supercapacitors, which can have multi-farad capacitance, which is what the C stands for, but they're not very common yet. All right, so let's talk about capacitors then. So we're going to talk about the simplest capacitor that you can imagine, a parallel plate capacitor. I had no idea that farads were named after Faraday. I assumed it was just some other guy. So in real life, just some words first. So in real life, we typically design objects that are called capacitors, and these are useful in electronics and for energy storage and so on. And so it's useful to be able to actually theoretically compute what the capacitance is of a system. So a capacitor is a thing that has a separation of charges that's proportional to the potential difference across those 2 conductors. A capacitor is basically 2 conductors that are nearby each other, and depending on the shape of those conductors and how far away they are, this capacitance, which is what C stands for, will vary. So it'd be useful to be able to theoretically predict, given some spatial configuration of conductors, what would the capacitance of such a capacitor be? So let's start with the simplest example. So this is our capacitor is made of 2 large parallel conducting plates, and they have area A. So the picture is we have one plate here, another plate here, both have area A. and they're separated, say, by a distance d. Okay? So we're going to make the assumption that, or we're going to allow ourselves to make the assumption that these are infinite plates, i.e. they're very large compared to the separation distance. So we can use the E field approximation for an infinite plate. Now, this is not actually correct. Like real world applications of capacitors have typically small plates because there's small electronic components. And so there are things called fringe effects, which occur like on the outs, like near the edges of the plates. But this is a decent approximation if your capacitor is big enough. So the smaller the contribution of your edges compared to the contribution from the meat of the capacitor, the more accurate this gets. So the question then is, how do we compute C? If we wanted to do that, how would we do it? Well, all we do is we just do a thought experiment. We imagine that we place some charge plus or minus Q on each plate. And then we compute the potential difference between those plates. And then we just end up dividing Q by that potential difference. It's just that easy. All we have to do is we just imagine the scenario, we figure out what the potential difference is based off of how the charges are distributed and so on, and that will give us a potential difference. Then we just divide one by the other. So because the plates are large and they're conductors, it's reasonable to assume that the charges are uniformly distributed over the entire area. So, and we also know that the electric field near a conductor sorry, that's not where we want to go yet. We're going to assume here, I know we're doing a lot of assuming, that the magnitude of the surface charge density, i.e. how these charges are assembled on each of the plates, it's just the total charge divided by the total area. It's just uniformly distributed. You have the same amount of charge in each square centimeter. But we also know, the electric field, this is something that we've calculated, outside of a conductor. We did this, I think, last week. It's that the magnitude of the electric field is equal to the magnitude of the charge density divided by epsilon naught, where sigma is the charge density on the surface of the conductor. In this case, this just is the charge density on the plate because it's just a plate. It doesn't have a volume, really. And so we can plug in what sigma is. So sigma is Q over A, so this is Q over epsilon naught A. So that's our electric field. That is the electric field at any point between these two plates. And we know the direction too. It points outwards because we're assuming that they're large. And we know that it's constant in magnitude because, again, we're assuming that they're large. So just to jot this down, the electric field is constant and points from the positive plate to the negative plate. Okay, we know the direction, we know the magnitude, so we can actually do a line integral now. So we want to do a line integral in the direction of the electric field, but the electric field just points from one plate to the other plate in a straight shot. So the potential difference between those two plates, i.e. from the positive to the negative plate, E dot dl, well, the electric field points in the direction that we want to go, which is straight from one plate to the other plate. So this is just the electric field, or the magnitude of the electric field, which is constant, so we can pull it out of the integral, times the distance between the plates. Basically, I just pulled this out and then just did an integral, a line integral, in a straight shot from one plate to the other, which is just the number d. And so we can plug in what we know E to be. E is Q over epsilon naught A, so this is QD over epsilon naught A. And so now we just have to rearrange. So by the way, what we found is that the potential difference is proportional to the charge, right? Like d, a, and epsilon naught are all constants. And so we find, after rearranging a bit, we find that Q is equal to epsilon naught A over D times delta V, and hence the capacitance C is given by epsilon naught A divided by D. Capacitance is just the thing you multiply delta V by to get the charge. So what this says, we can just think about this for a little bit, is that if you make the plates bigger, the capacitance gets bigger. Well, what does that mean? It means that for the same amount of, how do I want to phrase this? Yeah, so for the same potential difference, you have a larger amount of charge separation. And the reason that makes sense is because if you make the charge separation is, how do I want to phrase this? The line integral doesn't change, but if you make the plates bigger, you have more charge. And so you have more total charge separated because for a fixed surface, surface charge density, you would have more charge for larger plates, and so you'd have a larger charge separation. Similarly, if you increase the distance between them, then your capacitance goes down. How do we arrange it so V came into the equation? V is over here. If you increase the distance between them, then the charge separation, the density would be the same for a bigger plate, so there's more charge. Yeah, that's only true if we ensure that the charge density is fixed. But the bottom line is that it kind of makes sense that you'd be able to store more charge for a fixed voltage. That's really what this corresponds to. It tells you how much voltage it costs to store a certain amount of charge. If you make the plates bigger, you can store more charge for a particular voltage. If you make the distances bigger, you can store less charge for a particular voltage. So that's the way to think about it. And we'll do a lot more examples. We still have a few minutes. Just as something for you guys to see, this sort of calculation is done in the university physics textbook that I've been linking to, and there are 2 links under this bit in the lecture notes. So go take a look at that if you want after lecture. And also, just as a note of caution going forward, we're going to drop this delta V. We're just going to call it V when we're talking about a voltage difference. And it should be clear whether we're just talking about an electrostatic potential at a place or a voltage difference between 2 places from the context. But if you do have questions, do ask, and I can clarify. So that's the parallel plate capacitor. That is the capacitance for 2 large plates. It's just you multiply epsilon naught by the area of the plates and you divide by D. That tells you the capacitance. And you could go and you could make a capacitor like that, and what you would measure would be precisely or close to that value. All right, next thing. Let's do another example, just to prove that the capacitance is different for different geometries. So we're going to make another capacitor called the coaxial cylindrical capacitor. So let's just, so this is just the geometry of 2 cylinders that are stacked one inside the other, 2 conducting cylinders. This is going to be hard to draw. Let me draw the outermost cylinder first. So one of the cylinders is like a hollow tube, and the other one might be a rod, or it might just be another hollow tube. It doesn't actually matter. But it's a coaxial cylinder. Let's say that this one is plus A. Sorry, not plus A. Oh boy. So, God, I'm such a bad artist. This has radius A. Let's say that this one has radius B, right? And so we're going to put plus Q charge here on the inner one and minus Q charge on the outer one. Let's say this cylinder has length L, and that should be it for describing the geometry, right? So the way that we're going to compute the capacitance is the same way that we did before. We're going to add some amount of charge to one of the conductors and the same negative amount of charge on the other. So plus Q in the inner cylinder, minus Q on the outer cylinder. And then we're just going to compute the electric potential for that charge, for that amount of charge that's separated. And then we'll solve for the capacitance by dividing one by the other. So the electric field in this case is a little bit more complicated, but if the tube is sufficiently long, or if the tube is sufficiently thin, then we can use Gauss's law to find that between the conductors, the electric field as a function of distance, so R is 0 at the center and it goes out to B at the edge, is equal to Q divided by 2 pi epsilon naught R. Sorry, 2 pi epsilon naught LR. And it's just a relatively straightforward Gauss's law problem. Just use a Gaussian cylinder inside or between the two at some distance R, and then the enclosed charge would just be Q, and the area would be 2 pi RL, and then it's just a matter of solving. And it points straight out because these are conductors, right? So now because the electric fields do point straight out, they point perpendicular to the surface, computing the electrostatic potential difference is easy. It's just like before. It's just a product rather than an integral. So here we have that V, again, this is a difference now. We're just dropping the delta. This is an integral from the positive to the negative cylinder. When I say positive and negative, I'm talking about the charge, by the way. This is E dot dl. And so this dot product just becomes a product. It's an integral from radius A to radius B of the magnitude of E of R. Now, we can't factor this out because it changes with position, dr. So we're integrating from the inside cylinder to the outside cylinder. We're finding the path that we're taking is moving this way. This is our path L. Oh, that's a terrible letter. Oh boy. I will call that, actually I won't, I'll call this capital L. And this will be our path L that travels from one cylinder to the other. And so when we take the dot product, it's just dl just becomes dr. And so now we can just do this integral. So this is Q over 2 pi epsilon naught, capital L, from A to B of dr divided by R. And so the integral becomes Q over 2 pi epsilon naught L times the log of B over A. Okay, so that's the potential difference between those two plates, between those two cylinders. And so notice again that the potential difference is proportional to Q. So we can solve, because C is Q divided by V for a capacitor, that's always true, then the capacitance of this system is 2 pi epsilon naught L divided by log of B over A. That just is the capacitance. And so if you go back and compare this with the capacitance for the parallel plates, they're very clearly different. It's not just the area divided by the distance. It's like there's a different structure to the function. And so you can't just assume the capacitance of one thing is the same as the capacitance for another thing. You have to go back and compute it. But now that we know the capacitance for this particular configuration, if you were handed a coaxial cylindrical capacitor, now you know the formula that tells you the capacitance for that setup of conductors, and then you can use that to go and do useful things. There's an example that's in the place where I usually link you examples, university physics, where they do spherical capacitors, which, it's just more practice, so I would suggest that you take a look at it. It's linked in the lecture notes. Before we end for the day, I just want to tell you guys to go do a little bit of extra reading. It's like 2 paragraphs in the Liebherr textbook. I want you to go do some reading on work functions in metals. And where this reading can be found, this is somewhere in section 2.3 of the Liebherr text. It's not the entire section, it's like halfway down. So go take a look at that, read about that. It's not like we won't talk about it a whole lot, but it is a useful concept for you to have, especially because most of you guys will be engineers and work functions are super important for any sort of material business. So make sure to take a look at that. And I think that we'll just end the lecture here.